Hello, welcome to the COB channel. This is part 1 of Management Science. Today, we are going to discuss decision making. Decision theory is an analytic and systematic approach of the study of decision making. We have 6 steps for decision making. First, we define the problem at hand. Second, we list the possible alternatives. Third, we identify the possible outcomes or state of nature. Fourth, we list the payoff or profit of each combination of alternative and outcomes. Fifth, we select one of the mathematical decision theory models. Sixth, we apply the model and make our decision. Now that we know the steps, let us proceed to the 3 types of decision-making environment. The first type is decision-making under certainty. Here, decision makers know the consequences of every alternative or decision choice. For example, let's say that you have 1,000 to invest for a 1-year period. One alternative is to open a savings account paying 6% interest, and another is to invest in a government treasury bond paying 10% interest. If both investments are secure and guaranteed, there is a certainty that the treasury bond will pay a higher return, which will have a return of $100 for the 1-year period. For the next type of decision-making environment, we have the decision-making under uncertainty. Here, decision makers do not know the probabilities of various outcomes. There are 5 different types. First, we have the optimistic or maximax. It is used to find the alternative that maximizes the maximum payoff. Here is an example. First, we locate the maximum payoff of an alternative, which is $200,000 for the large plant, $100,000 for the small plant, and $0 for do nothing. After, we select the biggest number, which is $200,000 from building a large plant. Therefore, the decision would be to build a large plant. Next, we have the pessimistic or maximin approach. It is used to find the alternative that maximizes the minimum payoff. Here is an example. What we do to get a decision is to locate the minimum payoff for each alternative. For the large plant, negative $180,000. For the small plant, negative $20,000. And lastly, for do nothing, which is $0. The best option is 0, since it is the biggest possible alternative. Thus, it is recommended to do nothing under this approach, because we select the alternative with the maximum number. The third one is the criterion of realism or Hurwitz. It is a weighted average comprised between optimistic and pessimistic. To get the decision, first, we select a coefficient of realism or alpha. This is usually given in the problem. The alpha needs to be any number between 0 and 1. Please take note that if alpha has a value of 1, it is 100% optimistic. We compute for the weighted average using this formula. Weighted average is equal to alpha times maximum in the row plus 1 minus alpha times minimum in the row. Given the same example, first, we compute the weighted average for each alternative. For the large plant, we have $124,000, and for the small plant, we have $76,000. For the do nothing, we get 0. After which, we select the alternative with the highest value, which is $124,000. Thus, our decision would be to build a large plant. Next, we have the equally likely or Laplace. It considers all payoffs for each alternative. Next, we have the equally likely or Laplace. It considers all the payoffs for each alternative. In order to make a decision, first, we find the average payoff for each alternative by getting the average. For the large plant, the average is $10,000. For the small plant, the average is $40,000. And finally, for do nothing, the average is 0. After which, we choose the alternative with the highest average, which is to build a small plant, as our decision. Next, we have the minimax regret. It is based on opportunity loss or regret. We find the difference between the optimal profit and the actual payoff for a decision. To do this, first, we create an opportunity loss table by determining the opportunity loss for not choosing the best alternative. We do this using the equation opportunity loss is equal to best payoff in the column minus each payoff in the column. After which, we find the maximum opportunity loss for each alternative and pick the alternative with the minimum number. Here's an example. First, we make an opportunity loss table. We select the best payoff for each column. For the favorable state, we have $200,000, and for the unfavorable state, we have $0. After, we subtract each value in the table with the corresponding best column payoff as shown below the given. In here, we see the results. We select the highest number for each alternative. $180,000 for constructing a large plant, $100,000 for constructing a small plant, and $200,000 for do nothing. After which, we select the lowest number among all the highest numbers. Therefore, we choose to build a small plant with a value of $100,000. The last type of decision-making environment is decision-making under risk. Here, the decision maker knows the probabilities of the various outcomes. The last type of decision-making environment is decision-making under risk. Here, the decision maker knows the probabilities of the various outcomes. One popular method used is to choose an alternative with the highest expected monetary value or EMV. The formula for EMV is shown on the screen. So here, given the previous example, we need to compute for the EMV using the formula given a while ago. We can compute the EMV by multiplying the probability with each of the expected outcomes. For the EMV of the large plant, we multiply 0.5 and 200,000 plus 0.5 times negative 180,000, which will result to 10,000. For the EMV of the small plant, we multiply 0.5 times 100,000 plus 0.5 times negative 20,000, which will result to 40,000. For the EMV of do nothing, we multiply 0.5 times 0 plus 0.5 times 0, which results to 0. If we'd make a decision based on the highest EMV, we'd choose to build a small plant. There will be also times when we are given the choice to acquire information. To find if it would be beneficial for the company, we compute for the expected value of perfect information, or the EVPI. This places an upper bound on what you should pay for additional information. Moreover, it is also known as the increase in EMV from having perfect information. To get the EVPI, we first get the EVWPI, or the expected value with perfect information, less the maximum EMV. The EVPI is the long-run average if we have perfect information before a decision is made. There is a need to compute the best payoff for each state of nature because we don't know until after paying what the research would tell. So here we have the formula for EVWPI. We multiply the best payoff for each state of nature with the corresponding probability. Here we have an example. Given the additional cost of $65,000, is the information worth purchasing? So first, we determine the EVWPI. The best alternative for favorable state is to build a large plant with a $200,000 payoff. The best alternative for unfavorable state is to do nothing with zero payoff. From here, we could get the EVWPI, which is equal to 200,000 times 0.50 plus 0 times 0.50, which is 100,000. Now, we try to compute for the EVPI. The maximum EMV without additional information is $40,000, as computed a while ago. So now, the EVPI is equal to the EVWPI minus maximum EMV. That would be 100,000 minus 40,000, which will generate $60,000. Therefore, the maximum payment for information is $60,000. We do not purchase the additional information worth $65,000. Next, we have the expected opportunity loss or EOL. This is the cost of not picking the best solution. To get this, first, we need to construct an opportunity loss table. Next, for each alternative, multiply the opportunity loss by the probability of that loss for each possible outcome and add these together to get the EOL. Take note that the minimum EOL will always result in the same decision as the maximum EMV, and the minimum EOL will always be equal to the EVPI. Given the same problem, we try to make a decision based on the EOL. So first, we get the opportunity loss for each item. Again, the opportunity loss is equal to the best payoff in the column minus each payoff in the column. After which, we compute for the EOL by multiplying the probability with the opportunity loss for each alternative and corresponding state of nature. For the EOL of the large plant, we have 0.5 times 0 plus 0.5 times 180,000, which is equal to 90,000. For the EOL of the small plant, we have 0.5 times 100,000 plus 0.5 times 20,000, which is equal to 60,000. For the EOL of do nothing, we have 0.5 times 200,000 plus 0.5 times 0, which is equal to 100,000. Since we are talking about losses, we choose the alternative with the least opportunity loss, which is to construct a small plant. Therefore, our decision would be to construct a small plant. This is the end for this episode. We hope you learn more about decision making in this video. Thank you for watching and stay tuned at the COB channel for more videos. If you have any comments, questions, concerns, or feedback, just put a comment in the section below. Give us a thumbs up and subscribe.